Okay, so this video is going to be about electric potential energy. And it's like the regular potential energy that we know and love, but it has to do with these electric charges that we've been dealing with for a couple of weeks now. So if we think about this charge sitting here, maybe it's a positive charge, then what we talked about in class is that we have this electric field that goes out in all directions from this positive charge. Well, what happens if I want to bring maybe a second positive charge nearby? Okay, so I'm not saying that it's there already. I'm saying that it's nearby, and we want to bring it in. So I'm draw it a little bit bigger. Here's our original positive charge, and I'm going to bring this positive charge, and I'm going to bring it close in. Well, the thing is that these positive charges, they don't necessarily want to be next to each other. We know that according to Coulomb's law, we're going to have this repulsive force that is going to occur between the two. So really, what's happening here is that there's a force that I have to work against, and it is this electrostatic force that is being repelled away. So that means if there's an electrostatic force this way, that means I have to produce a force this way. I'm going to call it the applied force, and I have to bring it in. Okay, so let's say I'm bringing it in from just really, really far away, where it didn't really have any kind of influence from this first charge. I'll call that charge A, and then this one will be charge B. So I'm bringing charge B in, so I have to exert a force, and that force actually is getting stronger and stronger the closer that I get by. Well, if I'm exerting a force and I'm exerting it through a distance, then if I multiply force and distance together, we know that equals work. Okay, it equals work for all the mechanical things that we did earlier, but it equals work here as well. But it's a little bit slightly different. So force times distance gives us work, and we have a specific force that I'm exerting through this point, bringing charge B into charge A. But we also know from a long time ago that when you have work, that is also equal to the change in potential energy. Okay, so a change in potential energy. So what's happening with this situation? I'm increasing the amount of potential energy that's involved because let's say with these charge A and charge B are next to each other. If I were to let go of both of them, then they're going to fly off in opposite directions. There had to be energy there for that to happen. That potential energy that's there, just in the sheer fact that these two charges are close to each other, they have potential energy, and you can release it and make it into kinetic energy when you let go. So, but potential energy we know is measured in joules, but we have this weird force that we're dealing with. So let's say the force, right, force times distance is K Q1 Q2 over R squared, and I'm multiplying it by a distance. In this case, I'm going to say it's R, the distance between the two charges. Well, you can see that one of these R's cancels out. Let me do that in a different color. Alright, so one of these R's will cancel out. So what we're left with is that the work involved is equal to K Q1 Q2 over R. Alright, K Q1 Q2 over R. So if we go back to this scenario, then the distance right here is R, and if I just multiply by the charges, multiply by the constant, divide by R, then that gives us the energy that's involved. But like I said, energy is measured in joules, so let's work out the units. So we have K, which is a Newton meter squared per Coulomb squared, right, times one charge, which is a Coulomb, times another charge, which is a Coulomb, and divided by meters. Now this time it's just meters, not meters squared. So coulombs will cancel out here, the meter cancels out this one, and we're left with Newton meter, or force times distance, which does give us a joule. So this equation does give us energy, it gives us joules. So let's say we have a positive 5 coulombs here. Remember, that's a huge amount of charge. And then we have a positive, let's say 3 coulombs here, separated by a distance of 2 meters. Then we can say K times 5 coulombs times 3 coulombs over 2 meters. And remember that K is 9 times 10 to the 9th, right? And I'm just going to do this in my head. So let's say 5 times 3 is 15. 15 divided by 2 is, what, 7.5? 7.5 times 9 is, I don't even know, 7.5 times 9 is 67.5. So this would be 67.5 times 10 to the ninth, and that would be joules. That's a huge amount of energy. Of course, we're talking about a huge amount of charge here. So it's a huge amount of energy that would be just let go if these charges went the opposite direction. Now, if we wanted to know what their speed was right afterwards, then we would have to know what their mass was and figure out what the acceleration was, change in kinetic energy, all that jazz, just like what we did before. But we're not really worried about that right now. So what happens if we bring in a third charge? So let's say positive charge here, and I bring in a third negative charge. Well, what is this third charge? We're going to call that C. What does it have to work against? Well, in this case, it's not working against anything. It's being brought in by both A and B. So there's a force that's being brought in by A. There's a force that's being brought in by B, and that we know that B is going to be a stronger force because it's closer. So what is the energy that this thing brings to the table? Well, we already had K, QA, QB over R, right? When that distance is R, do that better. There we go. Now let's say that this distance is R as well. Then we're going to have to add in K, QB, QC divided by R, right? That's the energy just from this portion of it right here. But C is also dealing with A, so we have to add in KQA QC over 2R, because it's twice the distance away. Now in this case, that's going to be a negative, that's going to be a negative as well, because QC is a negative. So we're actually taking away energy from the situation by putting in a negative charge. And what does that mean? It just means when you let it go, there's not going to be as much energy because things are going to want to stay localized, being attracted to that charge there. So what we can say, and this is a very, very mathematical way of looking at it, is that your total electric potential energy would be equal to the sum of your Ks times all of your Qis times all of your Qjs over the distance between all of your I's and J's. Now, what does that mean? That means however many charges you have, could have 4 charges, 5 charges, then you have to take into account this pairing, this pairing, this pairing, this pairing, this pairing, this one, this one, this one, this one, and then finally this one. So how many terms would that be? Well, it'd be a ton, right? You have to go back and count them. But just for every charge that you bring in, you're going to be adding in one less terms than what you have charges. So think about that. If you had 2 charges, right? 2 charges all the way back here, then we ended up having one term, K, Q1, Q2 over R, or QA, QB. That's how I had it, right? But if you bring in a second one, or excuse me, a third charge, then all of a sudden we had this term and this term. So you brought in 2 more terms. If you were to bring in a charge D, then you'd have to add 3 more terms to it. And if you had to add a charge E, then you'd have to add 4 more terms. So the number of terms goes up with the number of charges that you have. But we always know that energy, being measured in joules, is a scalar quantity. Scalar quantity. So that means we have no direction associated with it, which means that let's say we have a charge distribution that looks like this, and this would be very, very messed up, right? Well, all you would need to know is the distances between each one of your particles with respect to each other, and you just plug it into the equation and add or subtract them. We don't have to worry about angles, we don't have to worry about directionality or anything like that, because it is a nice scalar. Energy is always a scalar. So it's very, very nice on us, so we don't have to worry about it with electric field or force. Energy is a scalar. And it just either adds or subtracts into it. Okay? Let's see, I think that's it for now. And that is just your electric potential energy in a nutshell. All right, I'll see you in class.